My name is Josh Gargan, and this is my presentation for finding the unknown mass of a black hole. The motion we have seen thus far has mostly been cases where the change in velocity was zero, but most motion we observe has multiple forces acting on a system, causing the change in velocity to be non-zero. For example, take an object that is following a circular trajectory and two of its velocity vectors are calculated, v1 and v2. Using this, we would be able to find the change in velocity. Now we can change our coordinate system to make it easier to understand how the velocity changes over the course of an object's motion. Take the tangent line to v1 to be the parallel axis, and we can see that a component of delta v lies on this line, denoted delta v parallel. And if we subtract delta v parallel from delta v, we get the second component of delta v, denoted as delta v perpendicular. With this new system, we would be better able to see how an object's velocity changes over the course of time. If delta v parallel is non-zero, that means there is a net force along this axis causing the object to either speed up or slow down. If delta v perpendicular is non-zero, that must mean that there is a net force along this axis causing the object to begin curving. We know that delta v, delta p, and the net force all point in the same direction. This means our diagram before, showing the components of delta v, is the same for the components of the net force, otherwise known as the change in momentum over the change in time. Now, if the interval of time between v1 and v2 is very small, then delta p over delta t would be approximately the derivative of momentum with respect to time. We also know that momentum is equal to the magnitude of momentum times the unit vector p, and with that knowledge we get the above equation for dp dt. The first component of dp dt is the parallel component of the net force, which points in the direction of p hat, and is approximately equal to the change in the magnitude of momentum over the change in time times the unit vector p, because delta t is small. The second component refers to the perpendicular component of the net force. When an object is moving along a path, there is a unique circle that is tangential to the direction of motion and has the same radius as the object's trajectory at that point in time. The derivative of the unit vector p with respect to time has a magnitude equal to the magnitude of the momentum times the magnitude of the velocity over the radius of the circle, and this force always points towards the center of the circle. For this lab, I used this knowledge of the parallel and perpendicular components of the net force to determine the mass of a black hole. Using the unique set of data points of the star's path generated from my email address, I modeled the trajectory of the star to determine what the mass of the black hole must be. I start off inputting the mass of the star we are given, and the delta t interval being equal to 1 day. We are given the code for calculating the x and y velocities and the initial and final velocities of the star. I then input the code for finding the initial and final momentum and the change in velocity and momentum. Using these two, I calculated dp dt and set this equal to the net force. I then proceeded to calculate dp dt parallel using the equations seen prior, and used the value of the parallel component to find the perpendicular component. The arrows for each force are set to be at the star's location and point toward the direction indicated by the force in that direction. The arrow scale is set to be an arbitrary number that makes it so that the arrows can be clearly seen through the simulation. In the simulation, you can see that the star begins speeding up as it gets closer to the black hole, and then slows down as it gets further from it. You can also see that the magnitude of the net force and the perpendicular component get exponentially larger as the star approaches the black hole, due to the fact that the velocity increases and the distance between the star and the black hole decreases. Also note that the net force always points towards the black hole. The parallel component points tangentially along the path of motion, and the perpendicular component points in towards the center of the tangential circle. I used the magnitude of the net force to calculate the mass of the black hole by manipulating the gravitational force equation. The error here was that each interval would give me back a different mass for the black hole. So to fix this, I found the average mass of the black hole through the simulation. The error is possibly due to assuming that the black hole is only affected by the force from the star, and that the black hole remains stationary through the simulation. In this lab, we said that the rate of change of momentum and the net force are the same when delta t is small, because this means that the instantaneous net force is equal to the rate of change of momentum. In reality, the rate of change of momentum is non-constant during the delta t intervals, and would not be equal to the instantaneous net force. If a different black hole was placed there, but the star's motion remained the same, we would not notice a difference because the motion of the star is directly influenced only by the gravitational force, and if the position data remains the same through the simulation, the net force must also remain constant, and thus the mass of the black hole. Thanks for watching.